All right, well, thank you for the introduction. Thanks again to everyone for coming here and obviously for setting this up and inviting us here. I want to talk about a novel type of reconfigurable system that we work with at Cell Matrix Corporation called the Cell Matrix architecture. This talk's going to be broken up into about 5 parts, basically. I'm going to begin with a sort of very high-level discussion of kind of the non-exotic features of a cell matrix. And if you've done any work with reconfigurable systems, or if you do, the cell matrix at this level will look similar to other kinds of devices that are out there. There's not a whole lot really unique that's going on at this level. But I'll give you this sort of high-level view, and from there I'm actually going to go and talk about a little bit of philosophy. And this is going to be kind of a backdrop that will come back and tie into the more unusual feature of the cell matrix, what we call the C-mode behavior of the system. And after I describe C-mode, I'll tell you some of the implications of that and how they relate to some of the things I described initially, some of the consequences of that. And then, if there's time, I'm going to talk about sort of where this goes in the future, some of the really weird stuff out there. Basic cell matrix features. And this is going to be a very brief overview, so I'll just kind of be skimming over some of the details. What is a cell matrix? Well, it's reconfigurable hardware. So it's hardware that has a fixed physical structure. It doesn't change, but you can change what the hardware does. Is this acting like an AND gate? Is it acting like an OR gate? You can change that after the system's been built by basically configuring the system, loading contents into memories inside. And that part, like I say, there's other devices out there that do similar things. The cell matrix is very fine-grained. It's composed of a large number of simple cells, very, very small-scale processors. They do things like single logic gate operations, a 1-bit adder, a multiplexer, a piece of a wire. These are the kinds of things that you do with your individual reconfigurable elements, as opposed to some systems where a single element might have a power PC inside it. Very, very fine-grained system, very simple, which is interesting in terms of manufacturing. A single cell, you can make it today with about 1,000 switches or transistors in it. So it's a very simple design. And it's meant to be a very general purpose system. It's got some of the flavor of things like cellular automata, but it's meant to be almost like a drop-in replacement for the engineering that you do today. If you can build circuitry today, you can map it onto a cell matrix very simply. So it looks and feels kind of like doing digital circuit design, doing standard engineering. Now, cells come in a number of different flavors. You can have cells with 4 sides, you can have cells with 3 sides, 6-sided cells. All of these are useful in different ways. They also come in different dimensionalities. There's 2-sided cells, there's 3-sided cells. You can envision hypercells with higher dimensionalities, but manufacturing-wise, you lose some features when you can't actually embed it natively into your space. Most of what I'll talk about in this talk will be 4-sided cells sitting in 2 dimensions. And the dimensionality has to do with the tiling of these things. So you basically take your cells and you just array them out in a big matrix. And in this case, we have 4-sided cells. Each cell has 4 neighbors. And inputs and outputs move from cell to cell exactly like you'd expect. Now, there's no direct connection between this cell and this cell. This cell only talks to its 4 neighbors, and that's the way the whole matrix looks. Now, the individual cells, each side has 2 inputs and 2 outputs. We call them C and D. 4-sided cell has a total of 4 sets of inputs and outputs. And there's a truth table inside which tells you how to map inputs to outputs. And for the first part of this talk, where I'm only talking about what we call the D-mode behavior, we're going to ignore the C lines. So a cell is just a 4-input, 4-output device. And the truth table just says, what outputs do I generate based on the combination of inputs? Okay, so for example, if you want to make a simple wire, you just want your Eastern outputs to match your Western inputs. These 64 bits are the truth table, and you just load it up however you want. In this case, we set all the outputs to 0, and we set the Eastern output to 1 whenever the Western input is 1. And it defines a wire. It's very, very straightforward design, very easy to automate and to work with. Now, because the cells are only connected to their immediate neighbors, you actually have an infinite scalability in the architecture. So if you take 2 4x4 matrices and you simply connect them along the edges, you get a bigger matrix out of it. And that's all you have to do to make a bigger one. You don't need to change anything in here. You don't need to make connections anywhere except at the edges. If you take 2 4x8s and connect them along the top and bottom, you get an 8x8 matrix. Architecturally, it scales perfectly. Now, there's issues of power distribution and things like that. But from an architectural viewpoint, you can just keep tiling this thing, making a bigger and bigger matrix. That'll be important in minutes. It also has a natural fault isolation. So this was a photograph of the first prototypes we built. which were actually in 1986. And you can see that there's basically this huge gap from cell to cell because this cell is connected to this only by 4 wires. And they're hard to see up here. They actually come out here, here, and here, and here. And that's it. And so when we got the prototypes back, we fabricated through a facility called Moses. And it's really inexpensive and kind of questionable quality. And we could actually look under the microscope and see like a solder blob or a metal blob on one of these lines and verify that that cell was not working, but all the other cells were still fine. So manufacturing-wise, there's hope that you can actually manufacture imperfect chips but still use them instead of tossing them out when there's a defect.